welcome. We were studying dual slope digital voltmeter, and so there were a few small blocks, okay, like a frequency divider and the integrator, most importantly, okay, and comparator. So these we have drawn as block diagrams. So we should also know how they are made or how they work. Now, comparator we already have studied in much detail. So this is basically a op amp just connected like this. One input to a fixed voltage, another is variable. The output is high if this input is higher than this, and the output is low if this input is higher than this. As simple as that. So we will not talk about the comparator. We will first talk about the frequency divider and then about the integrator. First, frequency divider, because it's easy. Okay, so let's talk about it. Frequency divider. What is it? This is nothing but a counter. We have seen it. Okay, so do you recall that we have drawn a ripple counter like this, which is made up of a number of T flip flops, toggle flip flops, and these are the T inputs of all these flip flops. These are their outputs, and we have clocks. These are negative edge triggered T flip flops. The way we made it is like this. Here we have given a clock signal input, which can come from a crystal oscillator or something, and then if this signal is like this, the toggle is always set to 1 or high for all of them. For all of them, they are connected to logic 1, level 1, and so therefore, every time a clock, a falling edge comes, this output Q toggles, okay, right. So the output Q toggles. Now, you know that I just recall it very briefly. So if this is time versus this clock, which is like this. Now this Q, call it Q0. Q0 will change its sign every time we have a negative edge, like here. So here it will become 0 to 1, then next time here 1 to 0, then next time here. Okay. So every negative edge will change the value of Q. So you see Q is also a square wave Q0 with half frequency. If this is f, this is f by 2, right. And then we connected this here. So this Q can drive this flip flop, call it Q1. So Q1 will therefore be changing its value every time Q0 goes from positive to negative, like here. So here we will have a, so this is Q1. Q1 is like this, this. Every falling edge of Q0 changes Q1. And similarly, Q2 will be like this, and you see this is f by 4, this is f by 8, and so on. So therefore, you see this is actually a frequency divider. If this is f frequency, this is f by 2, this is f by 4, this is f by 8, this is f by 16, right. So this is a frequency divider. Now, and this is what? This is also a modulo 16 counter. So if you think of it as one unit, okay. So you just think of it as one unit instead of thinking it as a combination of 4 units. Just think this is 1 unit. So this is the input and this is the output. So we have f input and the output frequency f by 16. Okay, so this is a modulo 16 counter. Okay, and call this output as y. So y, so how will the y change? Y will, so y has a frequency equal to f by 16. F is the input frequency, right? Now what you can do, you can connect this modulo 16 counters, a number of them, in cascade. Like you take one modulo 16 counter, okay, so this is this entire thing. Take another modulo 16 counter. So this is also same as this entire thing. Okay, now you can give this input here f. So this frequency y, so this you call y1, the output from this, it will have a frequency of f by 16. Now you can connect it to the next counter, okay, and then the output y2 will have a frequency f by 16 square, right. So if you think in this way, you will realize that actually these are modulo 2 counters, right. It's a modulo 2 counter because it counts 0 and 1. So one flip flop is just a modulo 2 counter. So note, one T flip flop is same as one modulo 2 counter. Okay. So in this way you can divide any a frequency into lower frequencies. Okay, and but this way you can divide only by 2, 4, 8, 16 in powers of 2, right. But if you want to say divide by 10, then what do you need? You need a counter that counts 0 to 9. So a decayed counter. So you need a decayed counter if you want to divide a frequency by a factor of 10. So let's take a decayed counter. This is modulo 10 counter, and in our first week of electronic instruments we have studied how a decayed counter can be made. I am not repeating for the sake of time. So here if you give a clock input whose frequency is f, the output will be f by 10, and you can connect few of them, many of them in cascade. So if you give a frequency here f, then this output will be f by 10, and if you are feeding this to the next counter, this will become f by 100. So this way you can take say 1 megahertz frequency and take 3 decayed counters in cascade, the output will be 1 kilohertz. Okay, so this is decayed counter, and okay. If you have any question, please write us in the forum. Okay. Now the next thing that we will look at is this integrator. This is the most important thing for a dual slope voltmeter. So let's talk about integrator. and this is a very important topic on its own. I will just first draw the integrator circuit. This is made up with an op amp. It looks like a non-inverting amplifier. So, you know what we have in a non-inverting amplifier? The negative is connected to the output, positive is grounded. Here we give the input, call it Vi, this is Vo. You can call it R1, R2. And then we know that the output Vo is Vi multiplied by R2 by R1. This is we know. Now, copy, paste, what we will do, we will replace this with a capacitor. Call it C. You can just call it now R, okay, because there is only one resistance. Now, I will just give you a way to remember this circuit, okay. That is, you just note that in Laplace domain, if you have studied that in any other course, we can write the impedance of a capacitor as 1 over Cs. The impedance of an integrator is Ls, capacitor is 1 over Cs, R is R. That is what you might have studied. And then this voltage in Laplace domain we will write as Vis, output as Vos. And if you just blindly copy this formula like this, Vos by Vis, and then in place of R2 we have 1 over Cs. So, here I write 1 over Cs, and in place of R1 I just have R, R1 is R divided by R. So, this is 1 over RCS. Okay. Now, from this you can write Vos is equal to Vis, and okay. So, Vos will be Vis divided by RCS, and if you know Laplace domain calculations from this, you can show that Vo in time domain will be Vi in time domain divided by RC integrated from say t0 to time t, this plus the integration constant which will be Vo that at t0. Okay. Now, this is some maths which, if you are not familiar with Laplace transform or this type of Laplace domain circuit, etc., it will be difficult for you to understand this, but those who know it, for them this is very easy. So, that is why I have told this, and I will I will explain this in a different way as well without using Laplace transform. Okay. So, but this is also a quick and dirty way to remember this circuit. You just replace this R with a capacitor C, and in Laplace domain this is 1 over Cs, and you know that so if you can first write the formula for inverting amplifier, replace R with 1 over Cs, and actually 1 by S acts like an integration in Laplace domain. Okay. So this is one way to remember it, but this is not quite satisfactory because physically we cannot see how the output is going to integrate this input. Okay. So this is quick and dirty maths, but physical intuition is more nicer than this. So let me draw this circuit once again. Say we will start the analysis with the assumption that Vi. So let's start with the assumption that Vi is equal to 0, Vo equal to 0, and this is Vn, Vp. Vn equal to 0, Vp is of course 0, this is not an assumption, this is connected to ground. Okay. This is Vi. Okay. So we start with the assumption that at any moment everything else is 0, input is 0, this potential is also 0, this is also 0. Is this a valid assumption? Is this assumption valid? Let's check. If this is 0, this is also 0, okay, and then from the static characteristic you know that if these two are equal, output can be 0, no problem. So you are not violating the static characteristic of the op amp, fine, no problem. Then this is 0, this is 0, so no current is flowing here, okay. This current here it will be 0 definitely, here no current is there, so definitely there will be no current in this branch as well, okay. So this current is 0, this is 0, this is 0, and if this current is 0, that means this capacitor is also not getting charged, okay. So the potential across the capacitor will also not change with time, so the this can remain in this configuration forever, okay. So output is 0, these two are equal, the static characteristic of the op amp is absolutely obeyed, maintained, and there is no current here because this is 0, this is 0, potential drop is 0 here, so no current here, no current of course through the input of the op amp, so that means this current 0, this current 0, so according to KCL this should also be 0, and if no current is flowing through the capacitor to the capacitor, then the potential across the capacitor will not change. If you are starting from 0 voltage, Vc, this voltage you can call Vc, okay. So if this voltage is Vc, this is also remaining 0, and so we will remain at this configuration forever, absolutely no problem, okay. So and yes, so this is a correct starting point where we can start our analysis. Now okay, yeah, let me just put plus and minus here. So this is my chosen reference direction to measure the voltage Vc, okay. Now say now I increase Vi, okay. So then so this is step 1, step 2, now we increase Vi slightly. Say Vi is equal to small voltage 1 volt. Okay. If we increase this slightly, then what will happen? A current, if this remains at 0, a current, let me call this is 1 ohm. Okay. This is also 1 farad. I mean large numbers, I am just taking this because for ease of calculation. Okay, this is not a practical number, of course non-practical, but just for ease of calculation. So this current, call it I, then I will become 1 ampere. So 1 ampere current will start to flow. So I equal to 1 ampere will start to flow, right. So if this current is flowing, and how will it flow? It will come to the capacitor only, okay, because it cannot go inside the op amp. So it will come to the capacitor only, right. So and that means charge is coming to this plate, and if we apply conservation of charge, then equal amount of charge must go out from the other plate. That will happen. That will happen. So whatever current is coming here, it will charge this plate, and equal amount of current will get away through the op amp, through the output of the op amp, like this. Okay. So this capacitor therefore will start to charge. So capacitor C will start to charge. So current is coming from left side. So left side will become positive. Left side will be positive, and right side will be negative. Okay. So this side will be positive, this side will be negative, and okay, according to my chosen direction, therefore Vc will start to become negative. So Vc will negatively increase. Because I have chosen right side to be positive. Okay, I mean, let's stick to that. I have chosen, so chosen. Okay, so Vc will negatively increase, and what will be the rate of increase? So we know the voltage Vc is nothing but the charge accumulated. It's proportional to the charge. Okay, so we know C is Q by V. So Vc is Q by C, and what is Q? Q is current I multiplied by, say, small time delta t, okay, divided by C. So the moment we increase Vi, after that this current will start to flow, okay, and after that, after delta t amount of time from the moment when Vi is increased, this will be the charge accumulated in across the capacitor, and this will be the voltage across the capacitor, right. So this is after delta t time. Okay. So let me draw. This is time. Initially Vi was 0. So initially Vi was 0, and then it is increased to some value. Okay, so this is Vi, and let me keep it like this. constant. So this is Vi. Okay, and consider a delta t amount of time. So within this delta t amount of time, okay, so some charge has come and it has charged this capacitor, and the capacitor voltage is increased by this much. Okay, so this is Vi, and let me draw. So Vc initially was 0, there was no charge across the capacitor. Now Vc is increased to some value. Okay, this value is I. So this height is same as this, I delta t by c. Now I is, okay, in place of I we can write Vi by R. So this is I, this is the current, right? So this is, so therefore this value, this height I will write this Vi by RC delta t. Vi by RC delta t. This is this height. Okay, this height. Now, so this curve, red curve is for Vc. How do I write? Let me write here. This is Vc. The black is Vi. And now let me draw what will happen to Vo. Let me see what will happen to Vo. Now at this moment, okay, so at this moment, at this starting, Vo was 0. Okay, let me draw that with blue pen. So Vo, here Vo was 0. Okay, so let me zoom in into this part. So here Vo was 0, and if we assume that Vo remains 0 even after this delta t time, okay, then what happens? Then you see, then after this delta t time, if we assume that Vo is still 0, okay, let me write, if Vo equal to 0 after delta t, then how much will be Vn? Vn is how much? Vn is Vo minus this voltage. Okay, then Vn is equal to Vo minus capacitor voltage Vc. So this will be, if it is still 0, 0 minus the current value of Vc, which is this. Okay, so this is negative. So you see this is negative. So this value is negative because we are assuming this is still 0, but this has got some charge. Therefore, if I add this voltage 0 plus this voltage or minus this voltage, I get a negative value here, right? And I have made a mistake. I have made a small mistake. I should have a minus sign. I have missed a minus sign here. Okay, because you know this voltage will be negative because left side is going to be positive, and but I'm taking the right side as my positive reference. So I should put a minus sign here, minus sign here, so everywhere. Okay, so this actually means this will go down. Okay, this is negative means it will go down. Let me correct it. Let me also draw it bigger. So delta T, I will take a big delta T. This is delta T, and this is how this voltage Vc will come down. So this height is same as minus Vi delta T by Rc. This is Vi, this is Vc, okay, and Vo, if we assume it is here still 0, then we see that Vn, okay, so everywhere here I will have this plus, so you see Vn here is positive, okay, because of this charge coming here, it will make Vn positive. Now if Vn is positive, this is greater than Vp. Vn is greater than Vp, and if Vn is greater than Vp, what happens to the output? According to the property of the op amp, the output will go down because Vn is greater than Vp. So output will go down. How much? Until and unless it has made Vn again equal to Vp. If output is going down, this potential is going down, then Vn is this plus this. So if this is going down, Vn will also go down, and again Vn will become equal to Vp. So at this moment, therefore, output will go down, making the Vn again equal to Vp. Okay, so Vo will go down, making Vn equal to Vp, which means now we know that Vn is Vo plus this Vc, so we know Vn, which is same as Vo minus Vc, this will become Vp equal to 0. So from this Vo will become just from this equal to Vc, which is same as Vi delta T by Rc. So you see that at this moment definitely the output of the op amp will go down and will make this again equal to 0. This is how the op amp will work. So even if you have assumed that, okay, after a small time this capacitor voltage is decreased, and therefore Vn has gone up. This is Vn. Okay, Vn has gone up. The op amp will change its output. It will bring down the output. So Vn will come down to 0 again. Right? I can think in this way, and then what will happen? This potential will be 0 again. Now you just follow. So this current will be again 1 ampere because this is again 0. So same current is coming. This will charge this capacitor further. Okay. So therefore more current is coming, and then this capacitor will get charged further. After some more time, this and if this capacitor is getting charged, if you think VO is not changing, then Vn will go up. So Vn will now try to go up like this. But if Vn is going up, then the output will go down, causing the Vn becoming equal to 0. So this will come down to 0 again. So this is how Vn will change. And these two things actually happen so fast, so that, I mean, although I have drawn it discretely that for some time Vn increases, then the op amp decreases the Vn, then again Vn increases, but it actually happens so fast and so smooth and so continuous that Vn increases slightly and immediately decreases, increases slightly, immediately decreases, increases slightly, immediately decreases, so that it looks like almost it's 0 always. This is how you can think it. So the output, Vn will remain always equal to 0. Okay? Practically Vn will always remain equal to 0. But the capacitor voltage will go down like this, and therefore the output VO will also go down. So let me just summarize. So we have seen that as current I flows, Vc becomes more and more negative, negatively charged, but the op amp simultaneously decreases VO to make Vn equal to Vp, and therefore and this happens so fast and so simultaneously, that means together, that Vn is equal to Vp always, almost always, right? So Vn remains equal to Vp, and then now the math is very simple. So now you look at the circuit, we know Vn is always equal to Vp, so this is always equal to 0. So now it's very simple, Vn is equal to 0, implying current I is how much? Vi minus 0 by R. This is this current, of course, always. This minus 0 by R, or 1 ohm. Okay. And this is the current, and this will imply that charge accumulated Q is Vi by R multiplied by delta T time. Okay, and this will imply that capacitor voltage is minus of this charge by C, which is Vi by RC delta T. From this it follows that VO output should be how much? VO is how much? Vn plus Vc. Vn plus Vc is VO. This is Vn plus Vc. So this is 0 plus, oh, I missed this minus sign again. 0 plus minus Vi delta T by RC. Okay. So from this, VO is equal to minus Vi delta T by RC. And then this is true for any t. Actually, this is true for any t, not just small delta t. This is because Vn is always 0. As long as I keep this Vi constant, I can write it like this. Okay, because Vn is always 0. Even if Vi is changing, actually, I can write this. You just think of it a bit. Only if you think, then only the picture will be clear. Okay, so I write like this: Vi multiplied by. No, but if I write this, then I have to do the integration. Okay, so I write like this: Vi, where Vi is constant, multiplied by this. And if you just think a bit more, you will immediately realize that Vo is nothing but Vi t integrated over time divided by Rc, even if Vi is changing with time. Okay, this analysis will follow. So I request you to think about it. Then it will be very funny and very interesting. Okay, and if you have question, you can ask. What else? And this is a quick and dirty shortcut that one can remember why this circuit acts like integrator. Just use the Laplace domain formulas. Okay. Okay, I guess that's enough for today. Thank you.